Good morning, everyone. I'm Stan. I'm a PhD student working with Dr. Phil. And my presentation today is about what I've been doing since our last workshop, 2024. So to do so, follow this outline. The first part of my presentation will be about the silicon carbide plate we got from the Army. So it's the same plate Anthony presented on. So I present what we were doing and the results in terms of microstructure and anisotropy. And the second part of my presentation will be, I will talk about the ceramic metal junction project I'm currently working on. I will present the objective, what we have done so far, and what we are planning to do. So the first part, assessing the microstructure and studying the anisotropy of silicon carbide. So silicon carbide is a ceramic well known for hardness, thermal conductivity, good resistance to corrosion, and chemical resistance. The main objective of the work we were doing here, the two main objectives were to explore the crystallographic structure of the silicon carbide plate we received, to determine whether the results were associated with the manufacturing process, and to explore also the anisotropy of the plate. And to do so, we conducted some compression tests. For the sample preparation steps, for the first part, the crystallography analysis, we prepared two samples, one following the normal direction and the other one following the transverse direction. So the transverse direction is the reference, no, was the normal direction for Anthony. Next time we should work on getting the same references. And for the anisotropy study, we obtained 30 samples, half following the normal direction. That's the plate top surface, and 15 following the transverse direction, so the side of the plate. For the results, last year when presenting, I presented this scan and these texture maps, where we can see that the plate is almost 100% alpha silicon carbide. That's the hexagonal phase of silicon carbide. And we also had this annular pattern, the texture map, highlighting a kind of strong texture on in the plate. And this doesn't really make sense when we know the plate was obtained through precious centering, so we are not supposed to expect any texture. That's why we re-index the sample, removing the beta silicon, the beta phase, that's the cubic phase. And when we did so, we obtained this more complete and reliable grain map with now randomized texture map. So the strong texture we were observing seems now to disappear when we get rid of the cubic phase. To confirm our result, we completed some XRD and Raman spectroscopy analysis also to confirm that we had like only hexagonal phase. And if we take a look, for example, at the Raman spectrum here, we can see that the plate is made up of 6H and 4H silicon carbide. Those are the polytypes of the alpha phase, the hexagonal. In terms of, for the compression test, in terms of anisotropy study, so as I said, we conducted compression tests with around 30 samples, 15 per direction. For the samples following the normal direction, we had a mean value of the maximum compression strength around 1.23 gigapascal. And for the samples following the transverse direction, we had a maximum compressive strength around 1.41 gigapascal, and with a reference value of 1.39. So even though there is this huge gap, statistically, we were not able to assume that there is any isotropy in the material, because when we conduct t-test, um, t-test statistics, statistics t-test on our result, they are still confident if we take into account that ceramics are full of defects and the sample were not flat also. So sometimes the sample were not only compressed, but some bending was also involved during the test. Okay. For the second project I've been working on, we have been working on, so, no, let me rephrase my, okay. So, the most common way is to join ceramics and metals nowadays are through coatings for cars and pipes, for example. And for massive parts, we use external assembly elements like screw and so on, or maybe adhesive. The main limitation with these techniques are the fact that they are usually employed for low temperature application. We might also face some leakage problem when using glue, for example, and there's a necessity of external element like screw. So the main objective of our project, no, to face this limitation, we decided to develop a novel technique for assembling massive ceramic parts, ceramic metal parts without any external element, and for extreme environment applications with temperatures above 1,000 degrees Celsius and with high mechanical stress. So far, we have defined the manufacturing techniques we're going to use to manufacture our junctions, ceramic metal junctions. So we decided to work with brazing and thermoconduction as they are diffusion bonding techniques. And in terms of materials, we decided to work with ceramic, with silicon carbide as ceramic and molybdenum and tungsten as metals. The main criteria for the choice of our metals were the melting temperature, the temperature of recrystallization, the thermal temperature, this is the temperature around which the diffusion bonding process starts between two materials, and the coefficient of dilatation of the metals that needed to be close to the silicon carbide, to the silicon carbide one. So in the next few months, and even currently, we are already working on studying the adherence of silicon carbide and the two metals. These steps consist of performing some metal deposition. We started a few weeks ago, but unfortunately, I didn't have some good results to present yet. But these steps consist of performing some metal deposition of these two metals on silicon carbide samples, and then we will measure the adherence of those two metals on the silicon carbide sample through scratch test, for example. And then we will start working on joining some samples, and then we will do some microstructure characterization and some physical and mechanical testing. We are thinking about in situ tensile test, in situ phase transformation post complete. Okay. So thank you, and feel free to ask me.
What are you using for the braids?
For the braids, we haven't defined yet, but the first technique we will implement is thermoconduction, direct thermoconduction, because we want to avoid a ternary phase. Like with brazing, we will need a third material, and that we create between the metal and the ceramic a ternary phase, and it might break the junction. In the literature, for all what we have seen, it's difficult to realize it with brazing because ceramics, according to thermodynamics, ceramics reaction with metals is really difficult, so when adding a ternary phase, it will make it more complicated. But we are still reading about it, but we will start with them.
Can you show me your compression test again?
Yeah,
So you're telling me you think these are the same number?
no, not that they are the same number, but that we were not able to say that the difference is, how can I say, significant, because these are just the mean value I represented. For some in the, for example, for some samples following the normal direction, we had values above even this 1.4. And it was, and we also had values really low, around 1 gigapascal. That's why I said, I think maybe I didn't present the result well. But
Your error bars are huge.
yeah, the errors bars are huge, but
So these are compressive tests. I've done compressive tests on
Yes.
ceramic, so the surface flaw issue should not be a very big deal in compression test. What becomes a bigger deal is the parallelism of the top and the bottom of your sample.
yeah, we had that problem at, like, if I come back to the for example, with Teagho oriented sample, we had that problem because to get the normal samples, we at the shop they were just cutting it, they played this way and we were done. But for the transverse direction sample, they were obliged to turn the plate this way and cut it through. So the samples were like, all the surface were not flat.
You have to spend a lot of time getting that right. or
Yeah,
you
polishing.
Can't believe your compression.
Yes.
Were these waterjet?
Yeah,
Cause I know when it cut, it kind of spreads out. And it gets
Yeah.
brown.
no, sorry.
I just want to point out, like, that just based on indentation, we see a lot of spatial variations in properties, so depending on where you're sampling, some of your variations are just coming from, not having consistent microstructures across the plate. There's a clarification question, I think, like, our terminologies in terms of orientations are consistent, because we're using the same thing, so when we say an indentation on an ND phase, you're doing indentation on the top surface.
Oh, okay, then I
I
missed
think- I think we're
I think
consistent in that
he was
respect.
presenting, yeah, sorry. Okay. Yes.
I have another just clarification question. So when you say you removed the cubic silicon phase, the silicon carbide phase, did you do that just mathematically by looking at the data you had, or did you do it by actually some type of treatment or process to remove it?
No, we did it using OIM software.
Okay.
So when you scan the sampling with EBSD, you will have the patterns of all the identified phase in the material. The problem here is that the cubic pattern were inducing a lot of noise in the overall patterns of the sample. That's why when we are indexing, if we first index with both phase, and then the result were just not reliable. So we decided to remove it because the system with spherical indexing, we were not able to identify the how can I say, good structure using the both phases in the system. So we did it with OIM.
Okay.
Yeah, just re-edit.